Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are beginning to look at the area of carbohydrate chemistry. Carbohydrates include sugars, starches, and celluloses. Are very important biochemicals found in milk, cereals, bread, sugars, and all fruits. They represent the main source of energy for both plants and animals. Now, the term carbohydrate is actually derived from the empirical formula. That is, empirically, carbohydrates appear to be hydrates of carbon. They have the empirical formula carbon.H2O and some whole number, X. As a result of this, carbohydrates were thought simply to be water bound to carbon. However, we now know that carbohydrates exist as one of the following three types of compounds. They can be polyhydroxyaldehydes, and so that you might see an example of this. Let's try drawing an example of a polyhydroxyaldehyde. One you were familiar with from last semester. I'll draw a Fisher projection of it. Had the aldehyde functional group. And what you see here is the molecule D-glyceraldehyde. Now, last semester you were given D-glyceraldehyde when we examined stereochemistry in the course. D-glyceraldehyde. And it runs out of room. Perfect. Now, D-glyceraldehyde is a polyhydroxyaldehyde. That is an aldehyde functional group, and every other carbon has hydroxy groups off of it. Okay. The second possibility for carbohydrate is a polyhydroxy ketone. So polyhydroxyketones are also carbohydrates. Now, we didn't have this example last year, but it really extends from the molecule D-glyceraldehyde. I could envisage changing this molecule where instead of an aldehyde group, I had polyhydroxy. Okay. So here's a polyhydroxyketone. That is, every carbon has a hydroxy group except one, which has a ketone. This is probably the simplest ketone-based carbohydrate. It is the only example of a carbohydrate that lacks a chiral center. And you can see it's 1,3-dihydroxy-2-propanone. Right. Both are examples of carbohydrates. Well, I said there were three. What's the third example? The third example, of course, are compounds that can be hydrolyzed can be hydrolyzed to A or B. One of the unique features of these types of molecules, carbohydrates, is that they can polymerize. They can link up and form chains of individual carbohydrates, and that polymeric chain is also a carbohydrate. So if you have a long chain carbohydrate, a long complicated compound, and you can hydrolyze it into individual polyhydroxyaldehydes or polyhydroxyketones, you have a carbohydrate. All right. Now, based on this, what are the functions of carbohydrates? Well, there are three important functions of carbohydrates in living organisms. Firstly, they can be used as a storage form. For chemical energy. So a storage form of chemical energy. B, or secondly, carbohydrates serve as structural elements of cells and tissues. Structural elements of cells. And tissues. And lastly, but equally important, is they represent a carbon source for the synthesis of other compounds. They are the biological source of carbon. And let's write that out. For the synthesis of other compounds. And be clear about this, these are other biologically important compounds. For the synthesis of other compounds. Right. Now, starches are the storage form of carbohydrates in plants and cellulose. They represent the main supporting structures of trees and plants. And it turns out that these starches are the ultimate source of most of our food. Glycogen is the chief storage carbohydrate in animals. And we should make note of a special term, and that term is the prefix glyco. When you ever see the term glyco in front of a word, such as glycoprotein or glycolipid, this means there is a carbohydrate fragment on that protein or lipid. Glyco is the indicator that this molecule is partially composed of carbohydrate, and because of that may have unique functions. Also note that the terms sugar and saccharide are used as synonyms for the term carbohydrate. Both of these can be used to represent the term carbohydrate. So often, I will sometimes say saying the term saccharide or sugar. All three names can be used interchangeably. Now, there are three classes of carbohydrates. Okay? Three classes of carbohydrate. What are they? The first class is the monosaccharide. The monosaccharide. Now, monosaccharides are carbohydrates that cannot be hydrolyzed to simpler carbohydrates. They consist of single polyhydroxyaldehyde or polyhydroxyketone molecules. So this is the individual carbohydrate. Examples of these molecules would be D-glucose or D-fructose. We will be looking at these examples later on and their structures. Next is the oligosaccharide. The term oligo is a prefix that means few. Now, few can vary in number. For carbohydrates, few will contain about 2 to 8 monosaccharide units. Two to 8 monosaccharides. These are joined together by an ether linkage. Remember the ether functional group from last semester? The ether linkage is referred to, because it's in a carbohydrate unit, as a glycosidic bond or a glycosidic linkage. So this is called a glycosidic linkage. A glycosidic linkage. Okay. Now, oligosaccharides are obtained when you break down the larger polysaccharides, and specific terminology for different oligosaccharides exist. For example, disaccharides consist of two monosaccharide units and can be hydrolyzed to monosaccharides. So disaccharides are examples of oligosaccharides. They only have two monosaccharide units. And examples of disaccharides are sucrose, would be the most familiar one. Maltose is another one you may have heard of. And cellobiose. And there are others that we're going to look at. Now, if you increase the number of monosaccharide units, you just change the prefix. For example, if you have 3 monosaccharide units, you have what is called a trisaccharide. A trisaccharide can be broken down into 3 monosaccharide units, and they don't have to be different. You could have the same units in your trisaccharide. You could have 3 glucoses linked together, and you'd have a trisaccharide, or they could all be 3 different monosaccharides. Lastly, of course, is the polysaccharide. And what is a polysaccharide? Well, a polysaccharide consists of repeating units of monosaccharides linked together through the ether-like glycosidic linkage. But they can be very large molecules. They can have molecular weights from a few hundred grams per mole into the millions of grams per mole. They usually consist of only a single or 2 alternating carbohydrates in long linear branch chains. Often they'll have about 3,100 to 3,000 subunits. And examples of the polysaccharides are starch, cellulose, and glycogen. And there are others. And these represent 3 of the common. Okay. Well, let us begin by looking at the first category, the monosaccharide. Families of monosaccharides. In general, all monosaccharides have 3 features in common. All monosaccharides have a general formula CH2ON, as we've indicated already. This is where the term carbohydrate came from. What's interesting is N is greater than or equal to 3, but less than 8, typically. 3 we've already seen with the simplest examples of carbohydrates I gave you, such as D-glyceraldehyde. Had 3 carbons in them. Notice N is your number of carbons. The second feature of a monosaccharide is that it consists of an unbranched chain. An unbranched chain. The molecule is a straight chain molecule. Okay, so there's an unbranched chain. The last feature is all carbons have the hydroxyl group. Except one. And that one carbon has a carbonyl, a C double bond O group, which is referred to as a carbonyl group. Okay. Now, in the monosaccharide, if the carbonyl is an aldehyde, the sugar is often referred to as an aldose. If, however, the C double bond O is found in a ketone, the sugar is referred to as a ketose. Now, the terms tri, tetra, pent, hex, hep can be used to indicate the number of carbons in the molecule. So, for example, if I redraw my D-glyceraldehyde, so this is D-glyceraldehyde. Based on the nature of the carbonyl, I can classify this as a certain type of sugar. Where D-glyceraldehyde is the molecule's name, D-glyceraldehyde, I can, because I have an aldehyde group, refer to this as an aldose. More specifically, I can indicate the number of carbons. Okay? I can refer to it as an aldo triose. Aldo triose. Now, for aldehydes, the term triose has also been used. Well, you can guess what you would get, okay, if you had a different molecule. What if you had the ketone that we had drawn previously? What if you had this guy? How would you classify him? Well, if I was classifying him, he's a ketose. And with 3 carbons, that would be a keto triose would be an acceptable term for it. However, the abbreviated form triose cannot be used since triose, simple prefix tri plus os, refers to aldehydes. So they added UL in between to indicate that you have a ketone. So sometimes you'll see the term, instead of ketotriose, you'll see triulose. A triulose would mean a ketose, sugar. So the suffix ulose is often used in naming a ketose, where the simple ose ending is used to refer to an aldehyde. These terms, ulose and ose, are used when you don't use the prefix aldo and keto. Okay. Now this raises one last question regarding nomenclature. You'll notice the name D-glyceraldehyde, for example. Let's give you another sugar. Let's consider the molecule that I draw up here. Let's try this guy. This monosaccharide sugar has the name D-erythrose. If I was to classify the sugar, I could refer to it as an aldotetrose or simply a tetrose. That would be its classification. But here's the question. Why do we use the name D-erythrose? Why not name this according to IUPAC nomenclature? In fact, in biochemistry, we are going to find that they often do not use what we would accept as traditional IUPAC nomenclature. They use this common nomenclature, where the stereochemistry is indicated by D and L and a specific name, such as D-erythrose. Well, in order to answer this question, let's use our methodologies for determining the IUPAC name. Now, the first thing I always do when I have to name something IUPAC is I find the longest carbon chain. I have 1, 2, 3, 4. This is a butane. The highest priority group is the aldehyde. That gets in the root. So this is a butanal. I can say butane 1-al, but aldehydes must be 1, so I can get away with just butanal, and that would be acceptable. I now have my substituents, which are hydroxy at carbon 2, 3, and 4. I have a trihydroxy, so I have a 2, 3, 4, trihydroxy. Butanal. Now, if I compare 2, 3, 4 trihydroxybutanal to the word erythrose, it's a bit longer, but it's not totally inconvenient. Now, the next thing I can do is I can prioritize. And remember, I have to determine the chirality in terms of R and S nomenclature for each chiral center. And when you have multiple chiral centers, we learned you do this by considering each chiral center individually. So let's consider the first chiral center. I'm going to write this as CHO for the aldehyde. I'm going to have my OH here, my H, and the long chain I'm going to just indicate with a squiggle. Now if I prioritize, oxygen's higher atomic number than either carbon's, so he becomes 1. The carbon here has an oxygen off of it. This carbon has an oxygen. He now has a carbon. He has a second oxygen, so the aldehyde group gets number 2. And then the squiggle becomes number 3. That makes the hydrogen number 4. In order to determine in a fissure what is the chirality, I must move the fourth group to the bottom. So I move the H to the bottom. That puts the squiggle Ever have problems drawing a squiggle? There we go. Okay, my CHO is still on top. My OH is over here. Now I have 1, 2, 3. Number 4 is at the bottom. I now draw an arc from 1 to 2 to 3, ignoring number 4. If that is counterclockwise or to the left, it's S. So this guy is S. Because I did one shift, the original is the opposite. Therefore, the original was R. So this chiral center is R. We now repeat the process for the lower chiral center. And if I prioritize the oxygen's highest atomic number, he gets 1. Now we've got the squiggle. This carbon here has an oxygen. This carbon has an oxygen. He has a carbon. He has an H. So the squiggle becomes number 2. CH2OH becomes number 3. And my H is number 4. And what we have here, now if we interchange number 4 to the bottom, taking number 4 down to the bottom, put my CH2, OH here, OH over here, squiggle on top, 1, 2, 3, 4, ignoring number 4. I'll draw my arc from 1 to 2 to 3. Again, it's counterclockwise. This is S, so the original, therefore, is R. So this chiral center is also R. And what you see then here is that if I'm going to complete the name, at carbon 2 we have R, at carbon 3 we have R, so this is a 2R, 3R, 2,3,4 trihydroxybutanol. Now compare that to the name D-erythros. How did we know that erythros in this case was D? All we had to do is draw the fissure with the longest carbon chain vertical, the aldehyde at the top. You go to the chiral center furthest from the C double bond O, that's this chiral center. If the OH is to the right, it's D. If it's to the left, it's L. Now look at what we had to do to determine R and S for the 2,3,4 trihydroxybutanol. Clearly, the IUPAC methodology is more complicated, especially if we start adding more chiral centers. Suppose we had D-glucose, which has 2 more chiral centers, a total of 4 chiral centers. We'd have to figure out the chirality of every chiral center. Now, yes, there is a pattern to it, and you can take shortcuts, but it turns out that nomenclature like D-glucose and D-erythros is simpler to use, and hence, it has been retained. And in biochemistry, typically we do not use IUPAC nomenclature, standard IUPAC nomenclature. All right. Well, I think this is a good place to stop. We will continue next lecture looking at the stereochemistry of carbohydrates and examine the D and L nomenclature of carbohydrates, and then we'll give you a list of aldoses that you need to learn the names of. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. A short introductory Scribblecast. I thank you very much.